What makes hyperredundant robots so challenging to create? Imagine a robot that can twist, bend, and stretch in ways that seem almost impossible. These are hyperredundant robots, and making them is no simple task. Their high number of joints and links give them incredible flexibility, but that also makes designing, modeling, and controlling them very tricky. Unlike regular robots with just a few joints, these have dozens or even hundreds of joints, which makes their structure complex. Building each joint requires tiny, reliable actuators and sensors placed along the robot's body. Managing all these parts while keeping the robot lightweight and sturdy is a big challenge. If the actuators are not directly at each joint and instead use tendons or cables, the mechanical system becomes even more complicated. Kinematic modeling, which is figuring out how the robot moves, gets much harder with so many joints. The set of all possible positions the robot can take is called the configuration space, and for hyperredundant robots, this space has very high dimensions. Traditional methods that work for robots with fewer joints become slow or impossible to use. Some engineers try to simplify the problem by treating the robot as a continuous curve, like a flexible snake or an elephant's trunk. These methods need advanced math and lots of computing power to predict how the robot will shape itself. Controlling these robots is another big hurdle. Because they have so many joints, solving the inverse kinematics problem, finding the joint angles needed to reach a specific point, is very demanding. There are often many solutions, or sometimes none at all, which makes it hard to find the best way to move. Control algorithms must handle all joints at once, avoid obstacles, and optimize for smooth, efficient movement. This requires powerful algorithms that can process a lot of data quickly. Nonlinear behaviors and uncertainties also add to the difficulty. Soft or flexible hyperredundant robots behave in ways that are hard to predict with simple models. Engineers often turn to machine learning to help predict how these robots will move based on real-world data. But collecting enough data and making sure the system works in real time can be tough. Programming these robots is not straightforward either. Since their movements are different from human-like robots, they need custom algorithms and control systems tailored to their unique shapes and tasks. In real-world applications, hyperredundant robots are great for navigating tight spaces, performing delicate tasks, or avoiding obstacles in cluttered environments. But creating them requires a deep understanding of robot mechanics, advanced control strategies, and often machine learning. All these factors make their design and operation a complex puzzle, but one that opens up amazing possibilities for robotics in the future.